Okay, so I better deliver on this title here and not waste your time now. So let's do a cool example. Let's do something really neat. It is just an example, but in fact, these sort of ideas show up in various contexts. So what's the cool example? We're going to take an integral from Calc 1, a single variable integral that cannot be calculated in Calc 1 tools. Okay, cannot be calculated in Calc 1 tools. And we're going to do magic. We're going to calculate it using Calc 2 tools. So that's the cool example. So let's prove that the integral from minus infinity to infinity of e to the minus x squared dx. So this is an improper integral, right? It's not a bounded interval. It's not a bounded interval, so it's an improper integral of a single variable function dx, okay? And I want to calculate it, and the claim is that this integral equals the root of pi. Even this is cool. Why would pi show up there, right? It's cool already. Okay, so why am I saying that this cannot be calculated using Calc 1 tools? So let me remind you, I won't write it down, but let me remind you how we calculate integrals in Calc 1. Well, first of all, it's improper, so we have to replace this infinity with an m and take m to infinity, right? That's how we do improper integrals. The limit of the integral up to m, or in this case from minus m to m. And in fact, that's not accurate because you have to take it from, let's say, 0 to m plus from minus m to 0, right? Calculate each one separately and then take the limit as m goes to infinity, add them up. That's what you have to do, right? That's how you do improper integrals. Does everybody remember that? Okay. Now, why am I saying you can't do it? Once you get a proper integral, a definite integral, once you replace these infinities with a finite m, how do we calculate an integral? We find the antiderivative and evaluate it between the limits, right? That's the Newton-Leibniz formula. But we even mentioned in this course that this is one of those functions that doesn't have an elementary antiderivative. Okay? So no matter how far you look and where you look, you're not going to find a function whose derivative is this. So you're not going to be able to write the antiderivative at m minus the antiderivative at 0. Because there is no formula for an antiderivative. Okay? So this integral cannot be calculated in single variable calculus, or let's say with single variable tools or techniques. Okay, clear? Is it clear why I'm saying that we're facing a challenge here? Everybody? Okay, so what are we going to do? Well, surprisingly and very excitingly, we're going to solve it using two variables. So we will use two variables. How? So let's look at the double integral of the function e to the power minus x squared plus y squared. So this clearly somewhat resembles the previous integral, except now there are two variables, right? And let's do it over the domain. The domain is going to be a circle of radius a. A circle centered at the origin of radius a. This is D. This is the domain over which I want to calculate this integral. Okay? Now a good question would be why? Because it's going to lead to a solution to the problem we're tackling. And by the way, this thing is called the Gauss Integral, and it has a lot of applications in applications. I don't know if Gauss was actually the first one to solve it, but I'm guessing so because of its name. Okay, so let's calculate this and see why it helps us. So let's call this I for integral sub a, because this is a parameter here. Okay, so let's call it I sub a. For a fixed a, if we can calculate this, then this is just a number. Do you agree? Right? Okay. So give me a suggestion of how to calculate something like this. Hint, look at the symmetry of the domain. Another hint, remember we're discussing change variables. That's kind of the topic where... Let's change variables. Good, I like that. To what variables? R and theta, obviously, because that's the symmetry of the domain, right? So how do we change to R and theta? So in R theta, what's this domain going to be? R is going to go from 0 to a, and theta is going to go from 0 to 2 pi. It's going to be a rectangle in R theta, R between 0 and a, theta between 0 and 2 pi, right? The function is going to be e to the minus what? R squared. And what's missing? The star of the show in the previous clip, the Jacobian. What's the Jacobian for R? Good. So what we're going to get is the integral from 0 to 2 pi d theta of the integral from 0 to a dr of the function, which is now e to the minus r squared, times r. Aha. So this r is the Jacobian for change of variables to polar coordinates. Okay, good? Yes?
It doesn't matter which one is on the outside or on the inside.
It doesn't matter because it's a rectangle. It's not just any simple domain. It's a rectangle. You can do it in whichever order you want. Okay? Okay. Now because of this Jacobian, thanks to this Jacobian, this inner integral is no longer an integral which we cannot handle, but it's an integral which we can handle. And what's the antiderivative of this function? We did something very similar previously. So it's the integral from 0 to 2 pi d theta. And inside, it's just the function e to the minus r squared. What's the derivative of this? It's e to the minus r squared times minus 2r, right? The inner derivative. We don't want minus 2r, we just want r, so we have to multiply it by minus 1/2. Do you agree that that's the antiderivative? Evaluated between r equals 0 and r equals a. Did everybody follow this? Good? We did a very similar calculation in several clips ago when we discussed changing order of integration. There was this triangle, and when we calculated like this, we encountered this thing which we couldn't evaluate, and then when we integrated like this, it became something like this which we could solve. Remember that? Vaguely. Okay. So what do we get here? What do we get? So the integral from 0 to 2 pi d theta, there's no theta here. So the integral from 0 to 2 pi d theta is what? It's theta evaluated between 0 and 2 pi, so it's just 2 pi. Right? Everybody? So there's a 2 pi times a minus 1/2 times e to the minus a squared minus e to the minus 0 squared. 0 squared is 0, minus 0 is still 0. E to the 0 is 1. Good? And this could be simplified a bit, so 2 times 1/2 goes away, and the minus we can throw in, and we can write it pi times 1 minus e to the minus a squared. Do you agree? Everybody? So this IA, which is the double integral of this function over this region, the area under the graph of this function over a circle of radius a, turns out to be pi times 1 minus e to the minus a squared. Do you agree? And it depends on a. Obviously, if you make a bigger, you're going to get a different a here. So far, so good? Okay. Now let's look. So put this aside a second. We're going to return to it in a minute. Now let's look at another double integral of the same function, e to the minus x squared plus y squared, dx dy. But now I'm going to do it over a different region. Now I'm going to take the region to be a square, where this is a. So this is a square which is 2a by 2a. Okay, it goes from a to minus a and from minus a to a on both axes. Good? Everybody? Okay. So let's calculate this. And in fact, what I'm going to do now is not really calculating it, it's just rewriting it. Okay, and we'll see why. So I'm not going to change variables here. This domain is a rectangle. It's even a very simple rectangle called a square. So I can automatically write it as iterated integrals, right? So I can write it as the integral from minus a to a dx of the integral from minus a to a dy of the function. And let me write the function e to the minus x squared times e to the minus y squared. Do you agree? Everybody? Okay. Now, how do I do iterated integrals? I solve the inner one and work my way out, right? That's how we do iterated integrals. Do you agree that when I want to calculate the inner integral, this e to the minus x squared is a constant, right? It's an integral dy, so I'm thinking of a fixed x. Do you agree? So I can take this term, let's use some colors here. I can take this term, e to the minus x squared, and pull it out of this snake. Do you agree? Okay. So what I get is, now what I'm doing now is kind of very intrinsic to this cool example, but this is important what I'm doing now. Okay, this is more general than just this example. So make sure you understand the next two steps. They are important. So I get the integral from minus a to a of e to the minus x squared times the integral from minus a to a of e to the minus y squared dy dx. Do you agree? Good? Now what is this thing in parentheses here? Do you agree that this thing is xless? It doesn't depend on x. This is a number. Well, it does depend on the parameter a, but this is some number in a. This is a function of a alone. It depends on the parameter a. But for a fixed a, it's a number. There are no x's here. Do you agree? So I can pull this entire thing out of the outer snake. Do you see that? As far as x can see, this thing is a number. If you fix an a, call a 7. What's your favorite number? 7. See, I guessed. 32. Call a 32. So the integral from minus 32 to 32 of some function of y dy is a number. Do you agree? I can pull that number out of the integral dx. It's a number. Numbers, scalars, move freely in and out of snakes, right? Did you ever go to the zoo? Go to the cage where the snake lives and look at scalars. They move freely in and out. Okay, so this thing equals, this is important. You must understand this. E to the minus y squared dy, which I just pulled out. And inside I'm left with the integral from minus a to a, e to the minus x squared dx. So it's just the product of these two integrals. Do you agree? They kind of got separated. They're not really one inside the other. That was kind of fake. Okay? It's really just this. Do you agree? Everybody? But there's even more to that. Do you agree that when I calculate an integral of a function of x dx, it's the same number I would get if I would call the variable t? So I can write here e to the minus t squared dt, and it's the same number. Do you agree? I could write e to the minus, give me your favorite letter. Not in English. Theta, good, in Greek. E to the minus theta squared d theta. Okay? Do you agree that it's the same number? It doesn't depend on what you call the letter. So do you agree that this equals the integral from minus a to a, e to the minus x squared dx squared? It's whatever this number is squared. And it doesn't depend on whether you call the variable x or y or theta or t or whatever. Do you agree? Good? Okay, so let's collect all our observations. The integral of this function over a square 2a by 2a happens to be this, and this is very similar to our original Calc 1 integral that we want to calculate. The only difference is that here we're doing it on a bounded symmetric domain from minus a to a rather than from minus infinity to infinity. Do you see that? On the other hand, what we know is when we try to integrate the same function on a circle of radius a, we could actually solve it. It's this. Okay? Okay, good. So now let's take a new board and tell me if you agree to the following inequality. The integral from minus a to a of e to the minus x squared dx squared, this was the area under the graph of the function e to the minus x squared plus y squared over a rectangle, a squared, an a by a, a 2a by 2a squared like this. That was this thing, right? Do you agree that this thing is greater than or equal to IA? What was IA? IA was the integral of the same function over this domain, a circle of radius a. Why is that true? It's a positive function. E to the minus x squared plus y squared is a positive function. This domain is contained in this domain, right? The circle sits inside. So when you take the area under the graph of a positive function over a bigger domain, you get a bigger number. Do you agree? So does everybody agree to this inequality?
Why is it equal to?
It's not. You can say that it's strictly bigger because the function is not zero there. Okay? So this is true because the function e to the minus x squared plus y squared is a positive function over a bigger domain. Clear? Everybody? So this example is not here just because it's cool. It's because it kind of hides a lot of things that are important. Okay? Good? Okay, and this we know. We know how to evaluate this. We evaluated it. It was pi times 1 minus e to the minus a squared. On the other hand, this is strictly less than what I'm going to call I2a. What's I2a? It's the integral of that same function over a circle of radius 2a. Okay, so over a circle of radius 2a, big circle, This is now 2a. Do you agree that this square sits inside this circle of radius 2a? Does everybody agree to that? Because a is somewhere here, and it really sits inside. Do you agree? So, do you agree to this inequality? And this we also know. It's just this thing, but instead of a, you have to write 2a. Okay, so what do we get? We get pi 1 minus e to the minus 2a squared. Good? Okay. Now I'm going to cheat just a bit, and I'm going to do something that you were taught in Calc 1 was a big no-no, which is say that the integral from minus infinity to infinity of this thing is the limit as a goes to infinity of this. Okay? In general, it's not true. The improper integral from minus infinity to infinity is not the limit of the integral from minus m to m. You have to break it in 0, calculate both separately, and add them, providing they're both finite. Remember that? That's an important point. However, if you're integrating over a symmetric domain and you're integrating a symmetric, not a symmetric, an even function, then it is the same. Because you can say that this integral is simply 2 times the integral from 0 to a. Do you agree to that? Okay? So specifically in this example, what I'm doing now is legitimate. Okay? But it's specific for this example. It's not true in general. So specifically in this example, let me erase these. Specifically in this example, as a goes to infinity, this goes to the integral from minus infinity to infinity of e to the minus x squared dx squared. Okay? And this is in this example and not in general. Okay? Do you agree? Let's sandwich this business. Use the sandwich theorem. What does this go to as a goes to infinity? When a goes to infinity, a squared is way there at infinity, right? So minus a squared is minus, it goes to minus infinity. E to the minus infinity goes to 0. So this entire expression goes to pi, because e to the minus a squared goes to 0, 1 minus it goes to 1, so it's pi times 1. Do you agree? But so does this. This still goes to 0, so this entire expression still goes to pi. Do you agree? Therefore, by the sandwich theorem, this thing equals pi. And therefore, the root of this thing equals the root of pi. So let's write by sandwich e to the minus x squared integrated over r from minus infinity to infinity equals the root of pi. Good? So I think it's a cool example. I think that, and you'll see it in math, many cool things originate when people let go of the strings and cables that hold them and try to do things which are originally in a certain realm of mathematics or any science and try to take it to further realms. Okay? So whoever thought of this was obviously a genius. Okay? But once you do it, you can think of solving more things in the same pattern, in the same way. Okay? And many important breakthroughs finally happened when people stopped trying to solve a problem only where it's originally defined. So even if you encounter it in algebra, for example, the fundamental theorem of algebra. Okay? Do you know what I'm talking about? the fundamental theorem of algebra, that every polynomial of degree, let's say n, has n roots up to multiplicity over the complex numbers. Okay? That theorem, the proof of that theorem, in fact, goes through calculus, goes through complex valued function calculus. Okay? And is not strictly in algebraic tools. Okay? So, I'm just babbling. Okay, so this I think is a good point to stop our discussion of double integrals. And remember, what lied in the base of this thing is the change of variables. That's what enabled it. And coming up next, after you have your sandwich, triple integrals. More snakes. Okay, coming up next.